Conventional video projectors represent point sources that are well suited for viewing white light reflection or transmission holograms. They allow reconstructing optical holograms by using a digital image as a reference wave. Thereby, the reconstruction of the object wave can be controlled in terms of its spatial distribution, local amplitude, and, in some cases, its wavelength. High-quality optical holograms can be combined with interactive graphical elements by synchronizing the reconstruction of the holograms with the rendering process of the graphical components. This illustrates an explosion model of stacked optical layers that combine a transmission hologram with an autostereoscopic lenticular screen. By rendering in an appropriate illumination image, it is possible to reconstruct the object wave of a hologram only partially, leaving gaps where graphical elements can be inserted. Both reflection holograms and transmission holograms remain transparent if not illuminated. Thus, they can serve as optical combiners, leading to very compact displays. Graphical elements can then be integrated into the hologram from one side, while illuminating it partially from the other side. If autostereoscopic displays are used to render 3D graphics registered to the hologram, both holographic and graphical content appear three-dimensional within the same space. If depth information of both is known, correct occlusion effects between hologram and graphics can be generated. The reconstructed object wave's amplitude is proportional to the reference wave's intensity. In addition to using an incomplete reference wave for reconstructing a fraction of the hologram, intensity variations of the projected light permit local modification of the recorded object wave's amplitude. Thus, the illumination image is not binary, but encodes local intensity variations. This shows the same hologram as before with 3D graphical elements and synthetic shading effects. Shadows are cast correctly from the hologram onto the graphics and vice versa. A virtual point source of light was first located at the top left corner and then moved to the top right corner in front of the display. Moving the virtual light source and computing new shading effects can be done in real time. An interactive example is shown now. A desktop prototype serves as a proof of concept configuration and as test beds for experiments. Projector and autostereoscopic screen with eye finder are integrated into a compact unit. A force feedback device enables the user to virtually touch and feel the hologram and the integrated virtual models. Depending on the position of the 6 degrees of freedom stylus-like device, force vectors and magnitudes are calculated dynamically based on predefined material parameters of the corresponding holographic or graphical content. A consistent combination of graphical and holographic content can be achieved in real time. To achieve consistent depth and occlusion effects, depth information of the holographic content have to be determined. For small-scale holograms, conventional flatbed scanners can be applied to reconstruct the holographic depth. A LIDE scanner technology was used to scan multiple images of a hologram by placing the holographic film on top of the scanner window, leaving the lid open and illuminating it under different illumination angles for each scan. The geometric image distortion that is caused by the different illuminations is captured with a parallel camera model defined by the scanner. In this case, an analytical solution exists for computing depth information if the correspondences between 2D image projections are known. For integrating a holographic augmentation with a window-based desktop environment, the illumination image can be restricted to a known area that is defined by the positions and the size of a window. This allows it to temporarily minimize such a holographic window or to align it over the main focus while working with other applications. Like optical holograms, digital holograms can be multiplexed. This example shows 3 different partial views that can be observed by moving within the total viewing zone of 110 degrees. Updating the graphical augmentations depending on the observer's position supports a non-continuous surround view. Transparent and touch-sensitive surfaces can be used as front layer to support touch and pointing interactions. Volumetric multiplexed holograms are digital multiple exposure transmission holograms that contain static CT, MRI, or other volumetric datasets. The projected images are used to illuminate the hologram and to display colored stereo pairs at the same time. Volumetric multiplexed holograms can be augmented with interactive stereoscopic graphics by projecting images which carry the illumination information and the colored stereo pairs at the same time. Large-scale optical holograms require large-scale display technology for combining them with interactive graphical elements. Conventional desktop displays, such as desktop-size CRTs or LCDs, are not sufficient in this case. Projection technology allows generating images that are larger than the display device itself. Furthermore, the display devices can be located at a different position than the image. Consequently, projectors can be used for reconstructing the holographic content and for displaying the graphical content. This example shows the augmentation of a large rainbow hologram of a Tyrannosaurus rex skull with finite element simulation of cranial mechanics and feeding. This illustrates a configuration that applies to a shuttered projection screen to integrate graphics into the large rainbow hologram presented before. It is mounted behind the holographic emulsion. While 2 display projectors generate the stereoscopic images of the augmented graphical content, an illumination projector reconstructs the hologram as explained before. All 3 projectors are synchronized with the shuttered projection screen. This allows a reconstruction of the hologram only when the screen is in the transparent mode, and an augmentation only when it is in the diffuse mode. The left and right stereo images of the graphical scene are displayed with twice the frequency of the screen's shutter frequency. This is 100 Hz and 50 Hz respectively in our case. A tracked 2-lens stereo camera system was used for scanning the hologram's depth from multiple perspectives. The point clouds that result from each scan are merged into a common coordinate system to form the whole surface. Due to the complex topology of the final point cloud, automatic triangulation methods will most likely create wrong connectivities between points. This leads to a significant amount of manual post-processing. Instead of triangulating, the points are rendered as point primitives with appropriate radii to fill the gaps of missing surface information. Such a point-based rendering concept is referred to as splatting. Thus, a splat model is used for computing consistent occlusion and illumination effects in real time, as explained before. Just like computer graphics, holograms are being applied as tools to solve individual research, engineering, and presentation problems within several domains. Up to today, however, these tools were applied separately. The overall goal of this project was to combine both technologies to create a powerful tool for science, industry, and education.